Lesson 7-7 talks about non-conservative forces. So non-conservative forces, applied forces, friction are examples of non-conservative forces. So these forces, what happens is energy, it enters or leaves the system as the work of non-conservative forces. So the energy is no longer conserved. So basically what that means in layman's terms is, before we always say the total energy before is equal to the total energy after, and the total energy before is equal to the sum of the potential and the kinetic. So when we did Hooke's law and we had elastic potential energy, even though it's a sum of the kinetic and potential, it could be the kinetic 1/2 mv squared, it could be gravitational potential energy, mgh, and it could be the potential energy stored in a spring, 1/2 kx squared. But if there's friction, there's work done by friction. So the total energy before is equal to the total energy after. So when you write the equation, like on an FRQ on the AP exam, and there's friction involved with an energy problem, to get the point for writing it out, you would write like K naught plus U naught plus W naught is equal to KF plus UF. And again, this work other, depending on what happens, if it's positive or negative, like if you have friction and it's negative, then this side is not going to be equal to this, because if this is negative because of the work done by friction, then this side is going to be less. So that's what this lesson has to do with. So there's some examples on the worksheet, and I guess we'll look at the homework. So here's the homework. This is like a classic physics problem, because see how it has the R, so you have a change in height from here to here. So you would do conservation of energy from here to here, and then from here to here, I guess maybe this one has friction or something like that. So maybe we'll look at this one, because they have stuff like this all the time, and then maybe we'll do this one too. So we'll start with number 7. So number 7 on the back, it says a truck loading station at a post office. It doesn't even make sense. A 2-kilogram package is released from rest at point A. So at point A, this is released at rest, so I know if V naught is 0 at that point. So at this point, the total energy is going to be all potential and no kinetic. And now remember, with conservation of energy, if there's not friction, the energy here is equal to the energy here is equal to, any point. So then it says the radius is 1.6. It slides down the track and reaches B with a speed of 4. From point B, it slides 3 meters to point C where it comes to rest. What is the coefficient of kinetic friction? So I want to find mu on the horizontal surface, and how much work is done on the package by friction as it slides down the circular ramp. So I know the mass is equal to 2 kilograms, and I'm going to use conservation of energy. The height above the ground is going to be 1.6, because that's like the radius of the circle. So that's the same here, and I kind of show it to you in the picture. So first I'll write my basic equation. So I'll say K naught plus U naught plus W naught is equal to KF plus UF. So on the FRQ, that's a point for writing that. Now what I would do is I would say, well, what's going on from like A to B? So at point A, it's all, you don't have, the total amount of energy remains the same. So this is 0. And then at the bottom, at base level on the ground, this is 0. So mgh plus W naught is equal to 1/2 mv squared. So mgh is going to be 2 kilograms times 9.8 meters per second squared times 1.6 meters plus W naught is equal to 1/2 2 times 4 squared. So then you do all the math and everything. So 31.36 plus W naught, 16 times 2 divided by 2. Oh, I didn't have to do that. Just 16. So W naught is equal to 31.36 minus. So W naught is equal to negative 15.36 joules. But this is just part of it because I know work is equal to FD or Fx. So the work is the frictional force times whatever that displacement is. So now I want to find the frictional force. Why am I doing all that? Because the bottom line here is to find mu. And I know that mu is equal to F of F over F of N. So that's how I'm going to end up finding mu. So I need to know F of F. So W naught is F of F times that displacement. So F of F is equal to W naught over how far it goes. So negative 15.36 over 3 comes out to be 5.12 newtons. So this is, my mu is going to be 5.12 divided by F of N. So F of N is mg. So 5.12, and mu is unitless, so you don't care about the negative. So then it's 9.8 times 2. So 5.12 divided by 19.6 comes out to be 0.26. That's an easy one. So we're just doing the basics, and then we'll do some FRQs that are challenging. So number 8 has a free body diagram. So number 8, I guess I need new paper. Okay, so let's look at number 8. So it said a wooden box with a mass of 2 kilograms is placed against a compressed spring at the bottom of an incline that has a slope of 37 degrees. When the spring is released, it projects the block up the incline at point B, a distance of 6 meters, up the incline from A. The block has a velocity of 4 meters per second. The coefficient of kinetic friction is equal to 0.50. Calculate the amount of potential energy that was initially stored in the spring. Alright, so if I want to know any idea what's going on in this problem, I have to draw a free body diagram. Well, first I'm going to draw my what's happening picture. So here is the block. Did they give me this? Is this the height they gave me? I don't know. Oh no, I have to find that. So, okay, at the bottom I have the spring and it's compressed. So that's like point A. Then the spring goes and it goes up here, so we'll call this B. And they tell me that this is 6. So that's B. And this is 37 degrees. So I'm going to do conservation of energy from A to B. So the total energy, so I'm going to do the energy here and here. Now there's work done because of, does this one have, yeah, because of, they gave me mu, so friction. So, but I'm going to do conservation of energy from here to here. So even though they gave me this 37 degrees, I know this is 6, so I can figure out what H is. So H is equal to 6 sine of 37. So H is equal to 3.6 meters. But I'm jumping ahead of myself. What I need to do is I need to draw my free body diagram on my block. So here's my block. Here's my weight acting down. I have my normal force. Now, this is why it's important. Here's my sign convention always goes in the direction. The block's going up the incline. So my sign convention is going like this because this is the way it's moving. Why is that important? Because remember, my frictional force goes opposite the direction of motion. But before I can even do anything with summing forces, I have to redraw this. This would be my free body diagram if I want points. So then to solve it, Fn, Ff stays the same, and then I replace mg with mg cosine theta and mg sine of theta. Where do I start in this problem? Well, because I know we're doing stuff with friction, we're going to say K naught plus U naught plus W naught is equal to KF plus UF. So at this point, so this is really like A to B. So at this point, when it's compressed, it's all potential energy, so the kinetic is 0. So then we have U naught plus W naught is equal to 1/2 mv squared plus the difference in that height it goes up, mgh. What is this question? Oh, it says calculate the amount of potential energy that was initially stored. So this is what I want to solve for. So I want to solve for U naught. So U naught is equal to 1/2 mv squared plus mgh plus W naught. And then I'm done. The problem is I can figure this out because they gave me that this is 2, this is 4, and I know all this. What I don't know is the work done by friction. So, how do I figure out the work done by friction? Well, I know that we call it, so the work done by friction is equal to the force times the displacement, which is F of F times the displacement. Oh, I don't know F of F. So this is kind of, when you don't know what to do, you just say, you go to the end, what do I want to solve for, and you kind of work backwards, and then the problem solves itself. So now I need to know F of F, and that's why I need my whole free body diagram thing. With another color marker. Alright. So I'm going to look at my free body diagram. I need F of F here. So what do I know? Well, I know this D is going to be 6 meters. So once I get that, I'm home free and I can solve. So I know that F of F is mu times F of N. And then I look at this, and you can write summation of force. F of Y is 0, so F of N is going to be equal and opposite to mg cosine theta. So mu times F of N, which is mu times mg cosine theta. So this really isn't that hard. So then, what is 0.5 times 2 times 9.8 times the cosine of 37 degrees? So 37 cosine times 9.8 equals times 2 equals times 0.5 equals, so 7.8 newtons. Now remember, this is negative, but the work done by friction is negative. So F of F comes out to be negative 7.8 newtons. So now I know F of F, so I put that in here. So that's equal to negative 7.8 newtons times 6 meters, because that's the 6 meters. Remember, work is done in the direction in which the force is displaced. So my frictional force is being displaced parallel to the surfaces in contact, and that's 6 meters, the distance, and that's the direction. So 7.8 times 6 comes out to be 46.96. So we're going to say, call that a nice even 47. Then, once I get that, I just put it all in here and I'm done. and it's 8 o'clock at night. So 1/2 mv squared plus mgh plus w naught. So it's 1/2 of 2 times 4 squared plus 2 times 9.8 times 3.6 plus the 47, because this is negative, so the negative times the negative 47 comes out plus. That's a good place you can make a mistake. So let's see if we get the right answer. 16, so 16 plus 3.6 times 9.8. And we get 133.56, which 134. Yay. So sometimes when you're not sure what to do, you go to the end, and when you go to the end, you can work backwards, and the problem kind of solves itself if you don't clearly see what to do. And that's it. So we did 2 significant. You only have 3 real problems, and then you can finish the other one by yourself. And that's it. It's a little messy.